Mm. Hello. Hi.
Hi, good morning.
Good morning. My name is Philip. I will be today's moderator of this track.
Hi,
Uh,
Philip. I'm Orsalia. Nice to meet you.
Nice to meet you, Orsalia. I see you've come in like 15 minutes early. Do you want to
Mm-hmm.
just test everything, I assume?
Yes. So I just want to check whether everything is okay because I was now in the first session of stream 2. And for example, as participant, you don't see who is there or whether there are like questions from all the
Okay,
people.
so you were in the track too. Okay, so you know the technical difficulties. Okay.
Yeah. Do you want to share with me some preview? And meanwhile, I'm also trying to share my screen to see if this works.
Yeah, I was like in this call trying to realize what the problems are, and I'm kind of in contact with. So everything is working on the presentation part as far as on my end.
Okay, so you can see my presentation.
Yes, and the audio is crystal clear, so everything is good.
Okay, cool. The other thing I was thinking is maybe I don't know what is the policy if I could deactivate my camera during after the introduction and going through the agenda, just in case there is some freezing with the image.
Okay, yeah, that's no problem. You can turn off your cam.
Okay. And then in the end, because I have approximately 20 slides, let me check again.
Mm-hmm.
Yeah, 23. It could be that we will finish like a bit earlier.
Mm-hmm.
So I practiced it, and yesterday it was lasting like 1 hour and 10 minutes. So, in case there are no questions, I would also ask if the people could share their experience from their industries and their jobs about how they go with this topic. And in that case, will you be enabling the microphone for them, or how does it work?
I don't think I'm allowed to enable microphones for participants. I will check it with the support now. Give me a second. Hmm? Oh, hello.
Hi, can you hear me?
Vous- Can you hear us?
Yes.
Mm-hmm.
Okay.
Hi, Orsalia.
Hi, Book.
Uh, yes, Philip, what you asked me. Okay,
Mhm.
it's possible to unmute attendees. Just yeah, we need to manage that.
Yeah, okay. So yeah, I can just say allowed to talk. So
I mean, I think what is always very easy coming from teams is if we tell them to raise their hand, maybe, and
mhm.
then you could give the word to the people that raise their hands. I don't know if it is popping up on priority, the first to the second to the third, but like this, you will have an overview, I guess, who wants to speak.
Yes, I was thinking the same thing, and it seems that Zoom allows a pretty easy way to just allow one person to be unmuted. So I guess we'll be okay.
Mm-hmm. Okay,
Yeah.
super.
Okay, then I will need to leave you because I have a flight to Vienna in 2 hours, and then yeah.
Oh, last minute at the airport.
Yeah.
Okay, thank you and see you tomorrow.
See you tomorrow. Yeah. Bye.
Bye bye.
Yeah, I was really shocked he got into the call because I thought he was already on a plane.
Okay, so until we start, should we just mute and stop the video?
Yeah, I think that's pretty
Mm-hmm.
okay. So
Okay, cool.
we have started getting attendees. For those that are already in, just wait for like 5 to 10 minutes, and we will start with the lecture. Okay, hello everyone, and welcome to stream 1 of DSC DACH in 2024. My name is Philip. I'm a program coordinator at DSC Europe, and I will be moderating this talk. But enough about me. Our first speaker is Orsalia Andreou. She's a data scientist at Erste Group, and today she will be talking about navigating ML explainability. Orsalia, the stage is yours.
Thank you, Philippe. Good morning, everyone. I'm Orsalia. I'm working in Erste Group for more than 4.5 years now as a data scientist with a master's degree in applied mathematics. And for today, our key objectives would be to give you a global understanding of the topic of model explainability, interpretability, transparency, terms that are used usually interchangeably, but do have some differences as well. And we will be showing you a framework about how to approach the topic of explainability in your machine learning and general data science projects, going through also the most common approaches and providing you some further materials in case you want to deep dive into the topics. At the end of the session, we will have a Q&A round. And in case this doesn't work, I would also be very happy if you would be sharing your experience with explainability from the industries and the companies that you're working on, so we could actively discuss a bit more on this topic. So I will be switching off my camera so we don't have any issues with the internet connection. And we'll be jumping right into the topic. Our agenda for today is, first of all, understanding why explainability is a topic, briefly going through the regulatory landscape of raising awareness and transparency in the machine learning models, the business expectations that are surrounding the topic, as well as how to define our context of explainability. Then we will explore the differences between interpretability versus explainability for a model, looking into how to define our inputs, how the internal mechanisms of different machine learning algorithms are working, their decision boundaries, and then after we have already trained our models, how can we explore better the global and local model behavior that leads us to a certain decision making. The last part of the session is focused in some final thoughts about things that sometimes we forget as data scientists, and also the further readings that I promised, because in reality this topic is so broad and expanding so fast that there is really a lot of material for you to look into in case you are interested in that. So why is explainability a topic, right? Why do we need explainable machine learning models? First of all, we want to explain because we want to somehow control what these models will be doing. That being control implied by regulation, that being control due to ethical standards that we would like to impose, or general rules of conduct in our companies, but we do have a certain need to explain so that we control. Then we want to explain also so that we can justify why are we doing certain things, why certain models reached certain decisions, and stand behind those decisions in a confident manner. But also on the most positive side, we are looking into explaining in order to discover patterns in our data that maybe we haven't seen before, discover information that will help us take more informed decisions, and eventually explain to improve our machine learning models themselves through different ways of discovering interactions between our input features, underlying mechanisms in the models that could be further enhanced with the future redevelopments. So explainability is not only about just understanding, so we explain this concept and these models and their predictions to someone, but it's also looking very much internally in the mechanisms and looking to improve what we are working on. First, I would like to present to you the regulatory landscape. This is not going to be too detailed, but I think it is important to have a global understanding of why we need to do certain things, what frameworks exist. I hope you have heard of the AI Act that was voted and approved in the Parliament this year in March. But for those who haven't, it's a good read. And why is that? The AI Act defines what is an AI system, and the aim of the regulation is to provide some guidelines and limit certain practices that are not acceptable within the EU. Now, if we are looking into the definition for the scope of application of this regulation itself, you will see that as an AI system, we define to be a machine-based system that can generate outputs such as predictions, content, or recommendations that influence physical or virtual environments. If we take a step back and we think about this definition a little bit, you will soon realize that it's quite vague, or if you want, broad. So this means that most of the applications that you are probably working on, unless they are falling in the general purpose AI models that we will speak in a few seconds about, they are an AI system. So one way or another, they are falling within this AI Act, and it doesn't need to be a machine learning model per se. It could also be some automatization framework that you are creating, interacting with customers and users that could be needing to go through the assessment and the risk classifications that are exhibited in the Act. On the second part, in case your model was not already in the first definition, it will definitely be on the second, the general purpose AI models. And these are now models that are looking more into the direction of the large language models, defined here explicitly as models that are using self-supervision, display significant generality, and are capable of producing outputs that are performing a wide range of tasks. We exclude from this definition those AI GPA, general purpose models that are not yet placed into the market. Now, after understanding these definitions, the most important thing of the Act is actually the risk taxonomy that it provides. And here we have 4 concretely risk layers that are the unacceptable risks. These would be AI systems that are prohibited to be used in Europe and should be removed from production within the next months. On the other side, we have the high-risk systems. These are models, systems that may impact the user's rights and safety. A typical high-risk AI system could be a medical device, emotion recognition system that is not within the prohibited categories of the Act. Critical infrastructures like monitoring of road traffic and so on. Further down, we have the limited risk AI systems. These are systems that we still understand as having certain risk to them, but we don't have from the Act the requirements to go through the conformity assessment, have the full transparency obligations, and so on. Here we are looking into purely transparency obligations, and this type of models could usually be things like chatbots, systems that interact with humans, systems that generate or manipulate image, audio, or video, looking, for example, into the direction of the deepfakes. And on the last risk layer, we would be having the minimal risk systems. These are systems that we don't recognize as having any risk attached to them or any significant risk whatsoever. And this could be, for example, systems that understand and filter your email spam. Finally, on the general purpose AI models, this is a part that is currently still into discussion about creating the first code of practice that will detail the AI Act rules specifically for the GPA model providers. And in case you are interested or working in that industry and have input to provide, the consultation for feedback has been extended until the 18th of September, so you can still contribute if you want to. But why am I showing these things as a first step in an explainability workshop? Because most of these AI systems are subject to transparency obligations, and transparency obligations eventually, apart from having the need to document in a clear and understanding way certain things, it go to the direction of model explainability, model opacity, in which depth can you explain your machine learning or AI system results. Therefore, very relevant requirements for explainability are already placed through the law with the AI Act. The second law that is relevant for explainability of machine learning and AI system results is the General Data Protection Law, which is primarily focused on private individuals, has been formulated already some years ago, but here we define the things like the right of explanation, the right to not be subject to automated processing or to challenge a decision that was made for a certain individual, the right to receive transparent information in a way that is easy to understand. And except from directly saying that in case we are using certain type of methodologies with private individuals, we will need to give some understanding for the model outcomes. Here, it is also very important to pay attention to this easy to understand part, because, and we will talk a lot about this also in the next parts of the session, it's not the same trying to explain a machine learning model to a data scientist, someone who is perhaps already working in this industry and has a bit higher understanding of the complexities and the mechanisms, with someone who is just, for example, having their account in the bank and now they received a recommendation from an AI supported system and they want to understand why they received this recommendation and how are their data concretely used in training these models. So explainability here plays a role, and it will play a role in different levels. And finally, the business expectations. Here I have for you a survey that was performed from Gartner about AI in organizations. And you can see that most business experts need to have a certain level of explanations when they are asked to collaborate or support AI techniques. This percentage is 50% for organizations that are having a formally created AI team, but it rises to 70% of the experts when organizations do not have this AI or data science teams that would require a wide range of levels of explanations, from being open to cooperate but need to understand, to being skeptical, require high depth explanations, or even adversarial to the information and require total transparency to be convinced of the value that we are bringing with these systems. And this is something really important because usually we are not developing these models for ourselves. We are developing these models to service some business need, to service a certain customer group, to service the general public. And therefore, what these people are thinking, what our stakeholders are thinking, and what they are comfortable with is of highest importance, so that we ensure the acceptance of whatever we are setting into production. And just to tease a little bit your brain and continue on this thought for the stakeholders, actually there is no perfect definition for model interpretability at the moment, but this is actually very much depending on the context, depending on whether in your project you have regulatory requirements, which are your stakeholders, for who should your model be explainable, to which level should your model be explainable. And this is what I would like to explore. How can we define the context, right? Because so far I said that we have the regulation that says we should do something, and we have our business stakeholders that say we should do something, and then we have like thousands of methodologies about how to develop AI and machine learning systems. And all of these have different dependencies and different techniques about how to make them explainable. So you might feel a little bit lost. And defining the context is really important to help you move forward. We would do this in 3 steps. The first step is defining the problem that you are trying to resolve before you are able to understand in which level you need to perform the model explainability. What is the business ambition? What is the concrete issue that you are trying to solve? Let's take the example of I would like to have a model that is pricing real estate properties in Austria, because so far this was performed manually. And now I would like to have a model that supports my experts in this job. This is a business ambition. This ambition tells you already that, okay, I'm predicting prices, so this is like a regression model, so I can already limit my model choices towards a regression model, and then I will think later on how explainable this needs to be. On top of that, we have the strategic priorities. And you might think that strategic priorities are the same with the business ambition, but in reality they are not, because maybe your business ambition, or often they are not, maybe your business ambition is to provide a tool that supports real estate property valuation, but the strategic priority is to start introducing automation and machine learning supported processes in your organization. So it doesn't really have to do concretely with the ambition of creating a regression model, but it has to do with starting to innovate. And finally, the success criteria. What are these indicators, ideally quantitative, that define the success of your machine learning and data science project? These are the type of things that once the project is reaching the end of its life cycle, your stakeholders will be able to tell you, you ticked these boxes, I'm very happy with the job that you did, all requirements are met, and we can proceed to putting this model into production. These 3 things are on the core of kickstarting any data science project, and at the same time in the core of understanding a little bit the direction that we need to start to take towards explainability, because different success criteria and different business ambitions and different strategic priorities slowly start to narrow down for us the options or the frameworks within which we need to operate. On the second step, we have concretely what are our explainability requirements. First and foremost, of course, the legal framework. especially for me, coming from banking, this is something that you always need to be keeping in mind, and to be able to achieve the maximum compliance possible to the law. On the other side, we have what we started discussing also before, the stakeholder identification and the business expectations. Why is this important? Stakeholders for a data science project could be a variety of different business groups. So if we are saying that we are developing a model, keeping the example of the real estate valuation in Austria, first of all, you should check whether you are legally allowed to do this. And probably there is a legal unit in your organization that needs to understand what you are trying to achieve and give you authorization for this. It also needs to understand at the later stages of the project actually how the model is working, and say that, yeah, this is still okay, perhaps these are some additional requirements that we need to put on top, but you can proceed with that. Then you have people like your model owner or your model requester, the person who is directly going to own this model. It could be someone within your team, but it could be that you are servicing a different unit. And this is, for example, the same person or group of people that will define for you what is the business ambition and your strategic priorities. On the other side, if, for example, this model will be then deployed in some online platform and be openly available, not only for your internal evaluators for these properties, but also for private individuals, your stakeholders are already increasing to people that are experts in property valuation and have been doing this in the past, and maybe they don't want to automate it because they liked their job and how it was, and private individuals that rarely will have an understanding about how actually these models are working, or maybe they will not like what they see because these results will mean that they will need then to have a higher interest rate in their mortgage because their existing property is not valued as much as they would expect, and then go to the people in the branch and ask, why is this happening? And now, like, just by thinking about this example, we have identified already like 4 or 5 different groups of stakeholders with completely different levels of understanding of a machine learning model, but also it's not only about the understanding, it's about what everyone needs to understand, because a real estate evaluator will need to understand how these models are working if they are to trust them. But a legal person doesn't really care about how a model is trained or what are the weights and so on. It just cares to verify that legal requirements are in place and the frameworks are solid. So all of these define the business expectations when we are talking about explainability requirements and to which extent your models need to be explainable. And finally, last but not least, practical constraints, things that are often overlooked maybe, and then they hit you in later stages of the project. Implementation constraints, especially if you are working in internal infrastructures. Can these infrastructures support the most advanced machine learning model you have thought about? It really fits into your data, it provides you the perfect output, but it cannot be implemented, right? This is something, implementation comes towards the end of your data science project life cycle, but the limitations that it might create for your modeling decisions are there from the very beginning, and you should consider them and talk with these people early on in advance. Then resources. What is the time that you have available to develop this model? How deep can you go in terms of explainability? How much is the time that you have allocated purely for modeling? And what is the time that you are willing to dedicate based also on the business requirements and expectations on explaining your model results? And finally, the data. huge problem, garbage in, garbage out. You can have the knowledge and the expertise to define and the possibility, technical possibility, your project requirements are matching your ideas, and you really want to do this sophisticated thing, but the data cannot support this because there are quality issues historically, because the distributions are not really fitting to what you have in mind. There are subsamples that are underrepresented in your population. All of these things coming together are then helping you from as early as possible, my recommendation, to identify within which frameworks you need to work in terms of explainability. So what is an explainable model, right? I said that there is no perfect interpretation. It really depends on the context, what you need to do. But let's try to give some definitions. I promised we will be differentiating a little bit interpretability and explainability. So here we will be looking into interpretability as the extent to which we can understand the internal behavior of our model or system. We will be looking into things like input definitions, how are our features created, how explainable our features are themselves before even moving to the training of a machine learning model. Then looking into the internal mechanisms and representations of different algorithms. This is something that is often not shared with the relevant stakeholders, but it is a tool to increase the transparency and raise the trust towards what you are trying to build. Decision boundaries, how is your selected methodology, splitting your feature space, are your model, your data distributions supporting the choice of an advanced analytical technique, or could more traditional methods also support you in certain problem areas? Then explainability would be more about how do we understand do we understand the way this system arrived to certain conclusions. Here we will be looking towards global model behavior, understanding how the model, how sensitive, how stable the model is, how are the different features interacting within the model, what are the most predictive features or the features with the highest importance in our already trained machine learning model, and looking into the local decision making, what was the reason for specific decisions. But it is also important to understand that at least in the current state, there is a trade-off. And don't get me wrong, things are expanding very fast, and you can already read new findings in literature about inherently explainable advanced machine learning models. But usually you have to choose between interpretability and accuracy, looking into models with higher interpretability as being these traditional machine learning techniques that we are already more comfortable with, like logistic regressions, decision trees. And as we go upper and upper and looking into more accuracy, and we are willing to trade off our interpretability instead, we are looking into ensemble methods, neural networks, and so on. But the future is bright, and what is actually happening already in the research field is that you can see hybrid modeling approaches surfacing, or researches that are looking into how to define internal architectures that are preserving the explainability properties of simpler modeling techniques, and then something more fundamental, looking directly into our input definition, how can we define interpretable feature engineering? Let's go now one by one into these topics and start with our input definitions. Here, depending on how we want to approach our problem and how explainable we have hopefully already defined in our context that the features need to be, we could differentiate in 3 types of features. On the first side would be features that are already having a direct semantic meaning. This means they are connected to real-world concepts that people can understand. And this could be something like the color of or the size of an object in an image, demographic information for a given customer market. In our real estate valuation problem, it could be how many rooms your house has. Then we are looking into features that are derived from this initial set of data that you have available, and they are maintaining or not maintaining their semantic meaning depending on the way that you are going about creating them. So derived features that maintain their semantic meaning could be, for example, feature transformations or corrections due to data quality issues, due to seasonality adjustments, or things that are necessary for the specific model that you have chosen to do as a pre-step, like scaling and normalization, could be categorical variable transformations. These things are transformed features, but they are transformed features that we can still understand sometimes if just going back to the initial feature set, what they are about and what is the real world context that they are connected to. On the other side, though, as we are increasing the opacity and decreasing a bit the understanding of the feature transformations, we have those features that after transformed or after created, they don't have any more semantic meanings. This could be interaction terms, embeddings. For example, if I go back to the real estate example, let's keep this throughout our session. I would be having for evaluating a house in Austria, drivers like the total size of the house and the number of rooms. But during my feature selection process and the discovery of different interactions with my target variable, I actually found out that the multiplication of the number of rooms and the size of my property is a highly predictive factor that I should include in my model. Once I do this multiplication, of course, the result is not anymore being connected to a real world concept because we cannot understand what does it mean, number of rooms multiplied by number of square meters. And one of my favorites and usually controversial, principal component analysis, principal component transformations. Some people say that they maintain their semantic meaning if the input features are semantically transparent. In my opinion, they don't, because if you are trying to then transpose a principal component space back to the initial feature space, the interactions that you are receiving there and the feature importances are actually not corresponding to the real interactions with which your model was trained with. So things to think about: model explainability, interpretability, transparency, they are not happening only at the end of your project. They are happening from the very beginning when you are defining your context and already when you are defining your features and which type of features you are comfortable with using. Then we have the internal mechanisms. Everyone knows a linear regression. We have our modeling assumptions. We have a very nice linear formula for reaching our final results. And because of this nice linear formula that everyone understands, regardless usually of their background, no one really cares to say, but I want to look into how this model is trained. I want to understand what is the optimization process for these weights. If you wanted to do it, of course, it's like a rather easy to read diagram. You are initializing your regression model, performing some trials while trying to minimize your cost function and have the convergence until you reach the final model. But so far no one really cared to understand this thing. Now, when we are starting moving into more advanced techniques, here I have as an example the random forest classifier, people started to not feel so comfortable with, and they started not feeling comfortable with this. By the way, random forest is considered a black box model because now the context is a little bit more advanced. So here the formulation of the response is, in the case of a classification, an average of the different trees in your forest. In the case of classification, this would be the majority vote for all your trees in your forest. And even though the concept of a single tree is understandable, once we are going to the ensemble, people started feeling, okay, this I don't understand. I would like to understand how it works a little bit better. And here we see that if we are trying to drill down how actually a random forest would be trained, this is already a bit more complicated than looking into a regression training, a linear regression training. So here we would have also more stochastic things like choosing subsets of the data and subsets of the feature space every time we want to perform a certain split. At the end, pruning the tree and each tree until we are reaching the final forest. But still, if you want to deep dive into it, you can more or less understand what is happening. It is a black box model. It's not like something that you can put down 100%, but it's not something totally abstract either. And then we are moving into our more advanced things. On the top of our trade-off between accuracy and interpretability, we saw before the neural networks. So here it's definitely something, at least in my experience, that people are more reluctant in using unless it's very necessary or unless the context requires that you would be using such an advanced technique. There are still ways to describe how the internal mechanisms of a neural network are working, but already by looking into the equations for the decision making and the graphs in comparison to our linear regression, you can see there is a big difference. So here in this example, just to briefly go through it, you see that we have a neural network which is having one input layer, two hidden layers, and an output layer. During our forward propagation, we would be inputting the different features, multiplying them with the weights, adding the bias, activating it layer after layer to reach the final output. And then during the backward propagation, we would be calculating our losses, and we would try with the optimizers to adjust the weight. So after we perform these tasks 1,000 times, our neural network is finally trained and ready to be used. Still somehow explainable, but you see, for example, that the final output of an already trained neural network would not be a simple linear function, what you would see at the linear regression side, but here we are looking directly into linear algebra, and we are having something which is a combination of the weights in the certain layer multiplied by the outputs of the different layer, and adding the bias term for that layer, so we can reach the final result with the inputs being nested within this result of previous layer again and again until we reach the input layer. So quite complicated, still some level of transparency once you want it. Decision boundaries. The last very important thing to understand when we are talking about different machine learning algorithms, and here it's more specifically directed to classification tasks, is how are these surfaces or these hypersurfaces created in the multidimensional space. So here in the example of the logistic regression, following the approach of more simple, widely acceptable models, we would see that we have a simple linear separation of the space in two sides, which is depending on the coefficient and may be sensitive to outliers in case these exist in our data. Then if we are looking into a random forest classifier, you would see already that this separation starts to be more complicated, and therefore this will be, once you train your model, something that will be harder to explain if you are asked to do so. So here we are looking as the decision boundaries defined as a combination of the decision boundaries within each tree of the ensemble, and having all these typical rectangular shapes coming from the fact that we have a tree-based structure. Of course, the advantages here are that we can split the feature space or our data points much more accurately. For example, in case your data have circular effects, something that, like the linear regression, would not work out of the box at least. And then here you can be more robust to outliers because we are having this concept of averaging and having majority votes and so on. And finally, in the neural networks, now here you could play very much because the architecture is highly affecting also the formation of the space. As a pun, I included here that the logistic regression actually can also be seen as a single layer neural network with one neuron, and the sigmoid function, what we know. But in general, neural networks provide much more the possibility for much more sophisticated separations of space. The shape that this will take is dependent, of course, from the activation functions and also heavily from the model architecture. So in the bottom, the three examples in the slide show, for example, how adding additional neurons would impact the hypersurface for the decision boundaries, getting more and more accurate in the way we are separating our observations based on different classes. This is concluding the part of interpretability and understanding input mechanism, input features, internal mechanisms, and decision boundary formation for different type of methodologies. And now we will be moving forward to the explainability component, which is more connected to trying to understand how the model behaves after being trained, both locally and globally. So on the global side, explainability is important to understand not only the quality, but also certain limitations that you might want to oppose to your model. And here we would split it first to understanding the feature importance. Are the global feature contributions in line with your business expectations? Is what you see as a result plausible based on our previous understanding of this certain task? This can be performed either with out-of-the-box explainability and feature importance calculations that most models provide, but you could also use model-agnostic methods like LIME and SHAP. In my experience, the three are never the same because there are different underlying mechanisms about how we are calculating the feature importance. So also, when you are doing this, try to understand which calculation is the one that is the most interesting for your business case, which is the calculation that supports what you are trying to explain on the global feature importance. Secondly, we have the feature interactions, something that is very important and might also lead to misleading model results in case not discovered in time. We will talk about this a little bit later, but with the feature interactions, we are trying to understand what is the underlying structure in the model's decisions. How are the different features interacting with each other so that we can reach certain decisions? This can be implemented in your models either with first and foremost with partial dependency plots. I would say this is like one of the most common ways, but be aware that in case your data are correlated, the partial dependence plot cannot be fully trusted. Because in such a case, the computation of a partial dependence plot for a feature with strong correlation with other features would involve averaging the predictions of artificial data instances, and those are unlikely to be in reality. So eventually it can create great bias in the estimated feature effects. To support this, you can use on top the M-plots. So the M-plots avoid averaging the predictions of unlikely data instances, but they are mixing the effect of a feature with effects of all correlated features. So another attention point to be taken into consideration. You could, in the end, go towards the accumulated local effect plots or ALE plots in case you are already familiar with them. There you can solve the problem by calculating also based on conditional distribution of the features and differences in predictions instead of averages. And finally, the SHAP hierarchical clustering. This is basically provided by the SHAP package, and there you can plot feature importances with feature correlations, exploring also in certain extent the interactions of the variables themselves. Very important because, for example, if we are looking into models like XGBoost, extreme gradient boosting, there it could be once you are inputting correlated features into your models, XGBoost will actually attribute most of the importance in one of the features in the group of the correlated features. And in case that feature, for example, is not so understandable by business, or it's not so expected to receive such high importance by business, you will receive questions like, but this is a bit counterintuitive now. Why is it happening? And this plot will help you understand why this is happening. It could be that you have some correlations that you haven't discovered, and the model mechanism worked in such a way to create this effect. So you need to go back into your feature selection and fine-tune this, yeah? Next, we have our sensitivity analysis. So for sensitivity analysis here, we are looking into assessing the stability and the robustness of our model predictions. And the most common techniques that you can use is the change one at a time approach. Here is this is one of the most simple and most common approaches, and basically what you do is moving one input variable, keeping others at their nominal values, and then returning the variable to its nominal value and repeating for all other features that you have in your model. Then we have variance-based methods, and don't get me wrong, here I'm just showing you some highlights in case you want to deep dive into these topics. There is extremely extended documentation and research you can do, and it could be that not all of these techniques will be fitting your business case. So that's why describing the context and defining the context, what we discussed before, is really important. But I did want to show you still some highlights about how you can implement global explainability features. So variance-based methods, here we are talking about probabilistic approaches where we are trying to quantify the uncertainty based on thinking that the sensitivity essentially of the output to an input is measured by the amount of the variance that is caused to our output because of this input. And finally, the bivariate analysis between each input and output. Here, depending on how your data dimensions are looking, you could do simple visualizations that will help you understand what are the interactions between groups of features and your target variable. Finally, fairness and bias, very important things, not only to say that your model is producing solid results, but also to understand whether you should limit certain areas of the scope of its application. So here, when we are looking into fairness and bias, we are trying to understand, are the model results biased towards certain subpopulations in our data? Are there any limitations that we could not further improve anymore and need to be dealt with during implementation in a different manner? First thing that can support you in this assessment is the data quality, of course. Reviewing the data that you have available for your machine learning model, ideally not at the end. And this is again showing that certain concepts are a little bit overarching, and explainability is an end-to-end business and not something that you should think only at the end of your project. But making sure that, for example, there are no data errors for specific subpopulations in your data that would lead to misleading results. Then representativeness analysis. How representative is your sample for certain subpopulations? If we are looking, for example, into the real estate property valuation, right? This is the example I said I will be keeping. If we are looking into that and I want with the same model to price both houses and apartments, I would need to check that the sample for both houses and apartments is representative, and it's not only representative during my model development, it's also representative with my application. It could be that apart from these big segments, I would like to check how the sample is varying in terms of sizes of properties. Perhaps I only have very few properties that are super expensive and luxurious, and therefore for these properties, the model will actually not be able to predict so much, because maybe in the historical data, there are 10 data points in total. So how could it derive some sense out of this? So these are all things that you can explore while analyzing different subpopulations in your sample and their representativeness. And finally, model performance analysis against these different segments. It could be that you have done all the above and you have created now a machine learning model that overall has great results. But once you start digging a little bit deeper in different segments or in different subpopulations, you still find some issues. This has to do also with explain to understand and explain to improve your models, right? So it could be that for whichever reason the model is not generalizing well in certain areas, and it produces biased estimations, and therefore you would like to remove this segment from your scope of application, or maybe develop a different model for this specific segment because it's too different from the other part of your population sample. Looking into local decision reasoning, now here is something that I think most of you will probably be familiar with, so I will keep it brief. We are looking into how we can understand better single predictions, and the most commonly used applications here is the Shapley additive explanations and local interpretable model agnostic explanations, SHAP and LIME. They need to be taken into consideration with a grain of salt, always. It is important, of course, they are widely used, widely accepted, but it is important that we understand how they work and what their limitations are. So in terms of SHAP, here we are looking into both local and global explanations, which is supporting you with a wider variety of visualizations. You can explore your model results from different perspectives with SHAP, and you have all of it with nice visuals and in one package. It is also suitable for many different model types. Perhaps a trap here, be aware that as you are increasing model complexity, it could be that the computation will become increasingly long. We have experienced this in many different projects. It might say that the SHAP is explaining random forest models, but the moment you are increasing the complexity to an extent that it cannot cope with it, it could be that you will need more time to compute these explanations. It is model agnostic, as LIME as well, but it does take into consideration certain model characteristics, meaning the calculation is not done in a fully model agnostic sort of way. The calculation is slightly changing depending on your model structures, and it is more stable. Yeah, this is the case in comparison to LIME. LIME, on the other side, it is focused on local explanations only, which is, of course, also limiting the type of visualizations that you can have available for your model results. And it is in generally more suitable for simple model types. It is a truly model agnostic methodology, but it does display some instability because of this, because it creates the local approximations or during the process of creating the local approximations, there is a random sampling component that creates this instability. So in case you have seen it already, you know about this, hopefully. In case not, be careful when you are using it. And just so we bring now everything together, because we said we saw different aspects of how to make things more transparent, more interpretable, more explainable, but how does this work globally, since many things are interconnected, right? So here we would start with our need to understand, and depending towards which direction we want to go, if we are looking towards understanding our data in the first side, we would look into ways to identify different sample characteristics, understand our input definitions in a better way. For example, like this doesn't have to do only about defining the energy class of a house as one of the input variables for our pricing model, but also understanding, okay, but was energy class standard always the same throughout my historical data, or are there any adjustments I should take into consideration so that the model is not getting trained with data that are not relevant anymore, data that are having structural breaks, or the same variable itself is not consistent throughout the timeline of my development data. Then on the other side, we have our model, and here we looked into understanding our model architecture and its internal mechanisms. How are these models trained? How do they look like? the decision boundary formation, how are the models splitting the space, and finally the model behavior, that being global with our feature importances, the interactions, sensitivity analysis, the fairness and the bias of the estimations, and any limitations that we should be aware in order to responsibly set these models into production afterwards. Towards the end, the local explanations to provide a reasoning for why we made such a decision. Okay, so final thoughts. Hopefully it was not too dense and I haven't lost you. But I would like to say about some things we tend to forget. And this is that good machine learning practices are also supporting model explainability. And you should remember this. It's not about looking for those techniques, about how to concretely implement explainable machine learning models. It is also about following certain good practices and standards for the way that you are developing these models. And more concretely, model generalization. Under or overfitting your models will eventually result in misleading interpretations regarding feature effects. So, in case you don't want to be in the spot to explain to some stakeholder why these features don't make any sense, or why the model looked so good during development but is unusable once you deployed it into production, try to use things like out of sample, out of time, cross-validation techniques for the evaluation. This will minimize effects of under and overfitting, will further improve or will further emphasize on the stability of your model choices, and will also help you with explainability, as then you will have the possibility to explain true effects and not misleading relationships. Model complexity, something I cannot stress enough. Don't resort to black box complex models when interpretable models are sufficient for your use case. Define your context, understand what is the problem that you need to solve, but when the increased complexity is not bringing a statistically significant improvement in your results, there is no way to go in that direction. There is no reason to go in that direction. This will only make it harder for you to provide explainable results and require more time and effort from everyone, that being you as a data science or a business stakeholder trying to understand what his model is doing, trying to make sense about how to use the model or even implement this model into production. Estimation uncertainty. The outputs of our models are also random variables in a way, since they are generated based on a random sampling from the data. So take the model variance into consideration. Try to work with confidence intervals for your predictions, for your key metrics. Try to somehow estimate this uncertainty so that you make your stakeholders more comfortable, firstly, with what they are going to be using, make it more transparent, and avoid surprises along the way to the extent possible. Feature interactions, what I said, I would mention also earlier. Independence does imply that our Pearson correlation coefficient is 0, but features with the coefficient being close to 0 could still be dependent. So be careful of that. Undiscovered interactions may also lead to counterintuitive model predictions. Therefore, it is really, really important that you understand your data and your features and what is going on. It could be that after you have already completed your model selection, you may still discover some things that you didn't discover during the model discovery. That's okay. There is no perfect model. and there is always room for improvement. But the more you understand how these things are working, the better you will be able to justify the results in the more transparent and explainable way. And this will eventually also engage your stakeholders and make them trust you as an expert, and your model results be more open to integrate them in their everyday practice. And finally, I cannot stress this enough, causal discovery. Machine learning models are not designed to identify causal relationships. In case you want to do this, there are concrete methodologies how to go about feature selection in such a way that you are discovering the true causal effects between independent and dependent variables. But by default, sharp feature importances and ex post, after modeling is completed, trying to assign causal effects in variables is not correct. The sharp feature importance is not implying causal effects, and often we see that this is interpreted in this way either due to being unaware of the details behind the implementations, or because the terms are considered associated, or perhaps there is no more time for causal discovery, or causal discovery was not important to start with when this project was being built. But nonetheless, it should be communicated in a transparent way, and you should be aware of this. And finally, since I said that all of these topics have a wide range of readings that you could do, I just link here the highlights from my side. These are just highlights that can get you started. There are many more things to read, but if we are looking into the regulation and you would like to get more familiar with this, here I have the AI Act and the GDPR. When we are looking into interpretable machine learning models, we have the book for a guide on making black box models explainable. For causal feature discovery, in case this one caught your eye, there are two things I wanted to share with you. I'm also at the moment really researching this field and has caught my attention lately. So one is starting from the paper, selecting robust features for machine learning applications using multi-data causal discovery. And the other thing is a wonderful GitHub index page, which is having a list of many different algorithms for causality with data. Finally, for inherently explainable model architectures, what I said that we are currently also extensively observing in the research fields, a great starting paper is designing inherently explainable, interpretable machine learning models. And if you want to explore more about the common misunderstandings when we are interpreting machine learning models, and deep dive into that and question perhaps your already existing approaches and whether you really do it in the best way possible, you could start with a paper on pitfalls, how to avoid when interpreting machine learning models. Okay. So that was the end of the session for today. I would like to thank everyone for your attention, and I really hope to see you tomorrow and maybe chat a little bit more for these topics. And now I would actually like, let me turn my camera back on. And Philip, you are also here. Hi. Yeah, now I would like to give the word to the round, and in case there is anyone who would like to share their experiences with explainability in their organizations, or perhaps have some questions to answer, I would be happy to do so. And yeah, also see you tomorrow. I don't know if we already have questions here.
If you have a question, You can also raise your hand and I'll give you the word. Do we have any questions? Okay, if we don't, I'd just like to thank you, Orsalia, for a great lecture, and yeah, see you at DSC.
Thank you everyone, and see you tomorrow. Bye bye.
Bye bye.